another FRQ type problem that we're going to do together because I just want to make sure everybody's on the same page. I don't know what I'm struggling with here. Okay, sulfur tetrafluoride. How many electrons from each? 6 plus 4 times 7, so 28 plus 6? 34. 34. I was struggling with that simple math earlier. Okay, so 34 electrons. So we've got sulfur in the middle. Fluorine, fluorine, fluorine. How many electrons? If I give everybody octet, how many will this be? It'll be 32. 8 times 4 is 32. Okay. Okay, so if I give everybody octet, we got 32 electrons here, and everybody's happy, right? But we also have those 2 extra electrons. Where do they go? On sulfur. And like I said on the video, sometimes I don't see your dots, so if you circle them, that helps me a lot, or just make them very bold. Okay, so if you have to think about the 3D arrangement, think of yourself, and every bond needs to be as far away from each other as possible. So it's not tetrahedral. What are some of our options of expanded octet? The shapes. So octahedral is when you got 6 ligands. Okay, we don't have 6, we've got 5.
Seesaw.
Okay, so we can do seesaw, or what are some other 5 things? We got T-shaped that you could have. If that's T-shaped is if you have 3. Let's pretend my leg is one of these. Okay, if you got 1, 2, 3 true bonds, like true ligands, and then behind me are lone pair, then that would be T-shaped. Okay, so but we've got 4 ligands to work with, so it's definitely seesaw, like Abby said. So seesaw is where you've got. Oh, I should have built this one. Do I have this one built for you? I've got every other member of this one built. Seesaw. We're going to build one today. Anyway, it's literally like a seesaw, like 2 arms, and then my head and the leg, and it tilts back and forth like a seesaw. Okay, and this lone pair sticks in the back. Now, whenever you draw it 3D-ish, you got to work on this a little bit. But the structure would be like F to the side, F up, F coming out, F down, kind of to indicate in the equatorial region, there's going to be an F and an F, and the axial region, there's an F and an F, but then what's back here? Lone pair, and that's still in the equatorial region, because now what are the bond angles between the equatorial around the middle of the atom, of the molecule? What's the angle here? Right, because around, I can't really draw this to perspective very much, but this is 360. If you've got 3 things in the way, they break up at 120 each, right? Now 120 is a very good bond angle, so that symbol means bond angle. Bond angle for lone pairs because they're not so close up and close and personal. On the other lone bonded pairs, they prefer to be far away. Now, if you had to go this one from axial to equatorial, there's no choice. It's going to be 90 and 90, right? Most of the, from fluorine to fluorine and fluorine to fluorine from up and down, it's going to be a 90-degree angle. Sometimes, though, depending on the structure, depending on like the size of the ligands, the bonded ones, this lone pair can actually repel the axial one just a wee bit. So it could possibly repel this one. We get like 87 degrees and 87, but that's a kind of a special case. Okay, so what did we say the shape of this was for molecular geometry versus electron group geometry? Because the electron group geometry is the easy peasy one. There's like 5 standard ones you have to talk about. You guys have your papers in front of you?
Are you
Do the electron group first. Yeah. Okay, so trigonal bipyramidal is going to be like, if you're considering everything attached to that as an electron domain, there are 5 electron domains, 1, 2, 3 in the equatorial region, 1, 2 in the upper region and lower region, so it makes like a trigonal bipyramidal shape. So electron group's really easy. You're either tetrahedral, trigonal, bipyramidal, octahedral. I said tetrahedral. What am I missing? Linear. And trigonal. Oh yeah, planar if you're flat because you don't have any lone pairs. So yeah, those are really simple because there's only 4 or 5 you can do. So what do we just say was trigonal, bipyramidal? Okay, and that's counting everything equally. But if you count them unequally, where the lone pairs do some smooshing around, after the lone pairs have done their repulsing, then you have to say, okay, just looking at the bonded pairs, then you should see a seesaw. And whenever you guys get to your lab, you'll see that a lot better. Okay, the bond angles are the same though. Bond angles are the same all the way. All right, so I'm actually not going to do chlorine trifluoride right now. and bond angles. Okay, we're good. So that's a lot of, that was a good bit of review. Let's do some more. Let's do the resonance structures. Oh no, we just did this one, and I'm not going to do this for now. I'm going to go to resonance structures. I put down a lot of review to do today. Okay, so this one's a little small, but let's go for it. Nitrite ion and nitrate ion both play a role in nitrogen cyclochemistry, so they try to relate things back to like biological examples and environmental examples. Draw the Lewis structures for the nitrite and nitrate ion. Go. And I'll do this with you too, actually. I'm going to have to go small. What's the nitrite equation or formula? NO2 minus versus nitrate, which is NO3, 1 minus, right? So how many electrons here? We have 5 plus 2 times oxygen, which all carry 6, plus this 1 rogue electron, right? We got a negative charge. So we got 18 electrons to work with here. Yeah? Okay, so we have nitrogen, and then I'm going to go symmetrical here. Let's put an oxygen on each side. 2, 4 electrons so far. If we put octet on everybody, straight up octet, I'm not going to draw it yet, but it would be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. We would have 20 electrons if I just spaced them all out and put octet. Can't have 20, so what do I have to do? Double bond someplace. So let's put double bond on either side, right? And then go octet. 2, 4, 6, 8 around oxygen. 2, 4, 2, 4, 6, 8 around nitrogen. 2, 4, 6, 8. I keep doing that, I'm sorry. 2, 4, 6, 8 around oxygen. So total 2, 4, 6, 8, 10, 12, 14, 16, 18. Yay! What's still wrong with this though? You do what? Bracket. Thank you. Bracket and -1 charge, because overall it's got a -1. Okay. Nitrate. Now, well, I chose to put that. I'm just going to go ahead and talk about this. I chose to put the double bond on the right side. You could have equally done it on the left side, correct? So I'm going to make a bigger bracket and actually say, I'm going to try to draw a little small here. The resonance structure for this the resonance structure for the nitrite ion is equally possible. We draw a double-headed arrow to indicate that either one of these are the true Lewis structure, even though what's the actual truth about this? Right, it's an intermediate molecule. It doesn't look like this first one or the second one at all. There's a intermediate that exists. So let's go ahead and talk about this now. We know the negative charge must exist on both. We know these are going to be the positions of the nitrogen, oxygen, and nitrogen and oxygen, because the reason that these are the positions as is because the formal charges on all these are 0, 0, and -1. Which of these has a -1 in the first model? Which of these has a -1 formal charge? Anybody? Does remember how to do formal charge? Yeah, is it this oxygen, this nitrogen, or this oxygen, which has a -1 formal charge? Left or right? Left one, because I'm going to circle this in different color. If you take the number of electrons it should have, which is its valence number, minus the ones assigned to it on the Lewis model, which assigned to it means like this oxygen has 1, 2, 3, 4 lone pairs. That's all its own. It's not sharing at all. But assigned to it is half of this bond. The whole bond is not assigned to oxygen. You know, when we do octet, yes, we say it's surrounded by it because it's sharing, but half of it is assigned to it. So 1, 2, 3, 4, 5, 6. 6 electrons for an oxygen, which normally has 6 valence number. Okay, so all ones that got a 0 formal charge. Nitrogen, which has 1, 2 assigned to it, plus half of that one in these two, right? So total is, it's got 5 assigned to it. How many does nitrogen normally have? 5, so it's got an oxygen, formal charge of 0. And then this oxygen has 1, 2, 3, 4, 5, 6, half that, 7. So it's got 7 electrons assigned to it, when generally it's only going to get 6. It's got a negative charge. That has to be notified or notated, because that's how this whole thing is a negative charge. It's because the formal charges add up to -1. Okay, so those are resonance structures. These resonance structures exist as an intermediate, though. The intermediate has a bond length and a bond strength between what is present here. So I'm going to look at this one because I've already messed that one up. This is a double bond and a single bond. What's the true length of the bond between the NO and NO? It's an intermediate. So what's intermediate between a single bond and a double bond? 1.5 bond. Okay, so that one's really easy to see because essentially what you're doing is you leave the single here and a single here, and you split this second bond between the two locations. So half and half is a sign. Pretty easy. So that's now weaker than a what? Right, weaker than a double bond, but stronger than a single bond. All right, because it's an intermediate. So let's do the nitrate as well. Nitrate. So you get 5 plus 3 times 6 plus 1, is that 24? Yeah, 18, 24, okay. 24 electrons, so then we got nitrogen, oxygen, 3 locations. If you assign octet around each of these oxygens, that's 24, right? But nitrogen would only have 6 electrons if we don't give it a lone pair. So what do we have to do? Give it a lone pair or make it a double bond. Okay, let's see which one works here. Let's just start off with double bond. Let's just see. Double bond, 2, 4, 6, okay. 2, 4, 6, okay. 2, 4, because it's already got, octet now. And this nitrogen also has octet. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Score. Let's check formal charge. What's the formal charge on this oxygen? This one. I'm going to start with 2, 4, 6, 0, right? This one down here? -1 because it's got 7 assigned electrons, 1 more than it should, leaving a negative residue on it, right? This one also has a -1. So -1, -1. Nitrogen? +1 because it's got 1, 2, 3, 4. So it only has assigned to it half of those bonds. So +1. Okay, so we've got -1s and +1s. They offset each other to make the -1 overall charge that nitrate does have. But is there any other way to arrange this so that you have lower formal charges, like zeros, for example, yet still yield octet for everybody? Like you could do this whole let's make a, no you can't, there's no other way. I was going to say let's make a lone pair and then change up the bonds here, but then you have 26 electrons and you can't have more than octet on nitrogen because it's little, right? Hey.
Tara, quit skipping school. Avery was working they got the first two and then we go get it. I'm pretty sure I'm perfect. It's just literally first come first served. Daniel I threw ourselves in the ass.
We literally for one I don't even want this. I just wanted to get it.
I just had to wait. I didn't the thought of getting and I got it.
Okay. I'll tell you guys later. I got Teacher of the Year. That's on video too, so they'll know. Okay, that doesn't happen. That doesn't get told anywhere. Because I don't know when they're gonna have to.
When do you find out?
I don't know, like on email, like today.
Don't you get like a special parking spot?
Yeah. Like right next to our park right now. Okay.
Because you're already here
So,
at 5.
I'm here, yeah, we're early. Okay, so back to nitrate. This has a -1 overall charge. I'm gonna erase that. Okay, and then we have to finish this. The intermediate exists between this and another one that looks just like this, but a double bond down low, and another one that looks just like this, but the double bond's on the left side, right? So if you take that double bond that you went from here to here to here, and you split it up in all of its locations, what is the intermediate bond length? 1.33, right? Because you have to take this guy and break it up 1, 2, 3 places. You break it up 3 places, that breaks it into thirds. So bond length is 1.33 repeating, right? Bond, and its strength is lesser or greater than a 1.5 bond? Lesser, right? Okay, less than a 1.5 bond, and a double bond. Okay, so if you had to predict which will have the stronger bond, shorter bond length, then it would be the nitrate. And just by your prediction, it's essentially like what we just talked about. You have to say it's in 3 different locations. You break the bond into 3 pieces, and it's got a third of the next size up, the next bond up. Okay, that's resonance. And then I was going to tell you, let's do polarity, and then I'll leave you alone, okay? Polarity, because this is the last part of the, okay, I have to do melting points. I'll wait for my 3 people to get back for melting points, because that's now coming into play a bit more than it did with our atomic structures. It makes a lot of sense, though. It deals with intermolecular forces a lot more, and we have a lab on that, like, Friday? Yeah, Friday. And it's a teacher-led part and the student-led part. It's actually one of my favorite labs. Okay, anyway, let's do polarity. Lewis dot, chlorine trifluoride is polar, boron trifluoride is not polar. Why? Chlorine trifluoride has what on it, do you think? That makes it polar. A lone pair, right. So this one's got what, 28 electrons? So chlorine, 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24, 26, 28. Okay, so what is the shape of this guy? That's 26. Sorry, here's 20. Is that 20, 24? I lied. I'm sorry, I have to make these bigger. That's 24, 28. Okay, so now what's the shape?
T-shape.
T-shape. This is one that you have to not, you got to start getting in the groove and not looking at your stuff, right? Because you have to think about, where are these lone pairs going to exist? Axial or equatorial? Axial means they're at a right angle to everything. Okay? That's 90 degrees. If they're equatorial, yeah, they're 90 degrees to one thing, but what are they to these things? 120, right? Because there's, 2 of the fluorines are going to take the axial location. That's an H for some reason, okay? This is going to have and you're going to have fluorine, 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 and then you get all this space over here for the lone pairs. You have to be the molecule, okay? I will sit there and go, figure out where the stuff is and make those awkward faces, but the lone pair are going to be on the middle region, so they are 120 apart. And when that happens, you can definitely see there's an inequality of charge. This side over here, yeah, there's electrons all around here, but they're not. Those are all partially negative and partially negative, because the dipole points here, here, and here. They don't the top and bottom will cancel each other out, but this one right here does not get canceled out because there's doubly negatives over here. So there's a large pool in the electrons to the left, meaning this is very partially negative, leaving, if that's partially negative, this actually has to be somewhat partially positive. It doesn't seem as if it is because the dipole is pointing this way, but it's just I'm trying to represent the inequality here. So this one's polar, where boron trifluoride, what's its shape? Can you determine it in your head? What?
I don't know what I'm saying.
Huh? Trigonal planar, good, because boron has 6 electrons. No, not like boron. I just heard Trixie. I was like, what the heck? Okay, so boron has 3 electrons plus each of the fluorines, so total of 21, so it's 24 electrons. So when you add it up here, you can only have, and there's electrons all here. Okay, you can only have 24, so the boron is okay though because it doesn't have tab octet, it's a small guy, so it doesn't only need 6 electrons. So that one's got 3 equally spaced, equally pooling ligands that cancel out each other's dipoles, leaving it overall nonpolar. So these 2 things would have very, very, very different properties like boiling point, vaporization, stuff like that, which we'll get into. All right, does that ring a bell and clarify some of the stuff you guys worked on? Okay, I did see there were 35 views this morning, and then I watched it again, so I have 36 views now. So you guys, thank you so much for watching that, and if you need to watch some parts of it again, do so. All right, so there's that. The hour-long video. What? That means that some people probably stopped it, went back, and stopped it, went back. Like if you got halfway through it and they were like, "Screw this, let's go back."
No, I mean like when I first.
Or I have other subscribers that want to watch it. Nick,
God,
my dad, he watches my videos. He does. He's gonna watch this too. Okay, so the two things we're going to do today, Born-Haber process, because you need to review lattice energy a bit more, and it was on your reading guide 1, but I want to do an activity with it, and this will go in your lab notebook. There are 3 compounds, lithium fluoride, sodium fluoride, and magnesium oxide. Do the magnesium oxide one, and then be done. Okay? There are little green cards behind Jordan. All of you guys need one? Okay, so no, you guys can work in partners or triplets, okay? And then after that, you guys can start molecular modeling building. Okay, and that might not take 45 minutes. Okay, if you guys team up, work in threes, groups of 3, then that will get done faster. But as you build them, you have to sketch and like do the repulsive units part of the lab, and or take a picture. I don't really care what you do, but I have to check them off that you built them correctly, like with the angles and stuff like that. Okay, so try to be simulate the bonds and non-bond, not the lone pairs as best as possible. The reason I had to bring your textbooks doesn't have you start that, but we'll see how much we get done. Okay. Okay. Question.
Do you think the kids watch your videos?
My little kids, my honors kids.
No, like not you kids.
My dog watches them with me. No, I make my husband watch them though, because he subscribes to my channel too. Because I needed more than like 7. I've got like 30.